Good morning, welcome back to lecture 21 and the second lecture on the part of the statistical field theory course that concerns specifically statistical field theory, while in the first part we looked more on stochastic processes. So let's begin by reviewing what we did yesterday. Whenever it was, I recorded yesterday, so for me it was yesterday. We were beginning to discuss when it is appropriate to formulate a problem in statistical mechanics using fields rather than using coordinate degrees of freedom. So using a representation which is based on a function, which in this case for simplicity was a scalar function of the configuration space, for instance. It could be a function of more variables. It could be a function of space and time if I'm dealing with the time-dependent processes in, say, out of equilibrium statistical mechanics. For the sake of simplicity, for the time being, we're going to stick to the simple case in which we're interested in Boltzmann averages, essentially. Although there is much more in statistical mechanics than simply that. So we have a field. X is now not a vector in configuration space, but a vector in R to the, say, to the number of dimension of my system. So in particular, if you're interested in 3 dimension, it's 3, not surprisingly. Okay, and what we were discussing in the previous lecture is that a field representation normally is something you use when you have many degrees of freedom within a single elementary lattice spacing. The size of the lattice spacing is basically 2 pi times the cutoff. And this is the frequency cutoff, UV cutoff, at which you're setting your resolution of your statistical model. So typically you imagine you have a spectrum with a gap. You imagine you have a spectrum with a gap. Let me move this down for a moment. This is hard frequencies. These are infrared frequencies, or these are UV frequencies, as you normally call it. And then we set lambda somewhere here. And then the typical lattice spacing is of the order of 2 pi over lambda. So whenever we have a situation like this, if I can choose a lattice spacing, if the typical physics of my physical systems contain the spectrum, and this spectrum dictates the typical value of the lattice spacing, and in this lattice spacing I typically find several particles, many particles, a central limit theorem prone type of particle, then it makes much more sense to describe the dynamics with fields than with particles. Because the central limit theorem will work in such a way that within each cell the field will have, of course, fluctuations because it's a stochastic variable. But fluctuations will be moderate and self-averaging somehow. And also the plane number of degrees of freedom will be small if you use a lattice than if you use particles. And we commented on the fact that you can view the necessity of using field theory in quantum mechanics, in relativistic quantum mechanics, not in an additional way through this perspective, which comes in addition to the typical causality request in relativistic quantum mechanics, and is the fact that in quantum mechanics, where the number of particles is not conserved in the relativistic regime, then you have virtually infinitely many particles in any finite chunk of space-time, and therefore fields are the natural formulations for this kind of theory. Okay, then we moved on, and we used the effective theory argument based on renormalization groups that we introduced in the first prologue lectures on renormalizing the Schrödinger equation to arrive to a Hamiltonian in terms of fields, which I will write now in the following way. We were specifically considering the example of a scalar field, and I think I have a negative sign here, if I'm not mistaken. I think I have a negative sign because this guy, yeah, I got a negative sign here. I might be mistaken in the previous notes. I must have forgotten this negative sign. I'll come back in a moment on why I have a negative sign there. But we came up with this term plus like lambda phi to the fourth divided by 4 factorial. As a standard workable Hamiltonian to describe fields where there's some finite range correlation. So the argument there, let me remind you, is that when you divide the fields into lattices, what if you want to account some kind of finite range of neighbor type of interactions, you get like configuration I plus 1, interactions or like phi I plus 2. These guys typically enter in higher order derivatives. So whenever you have a field that can interact with itself, we have variables inside that interact among each other at a finite distance. This can be parameterized in terms of field through derivative operators. And each of these also sort of goes to renormalize the diagonal terms here, which simply comes from the fact that it takes a finite amount of energy to polarize the system in one direction or another. So you have a penalty. And then you have 5 to the fourth or 5 to the cube. And we argue that the odd terms in the Hamiltonian, if this is supposed to represent a spin system, for instance, then the odd terms in the Hamiltonian are arguably not there because they don't reflect the fundamental system's symmetry. Because if you reverse the magnet, then of course you're supposed to get the same physics unless you have an external magnetic field. Now, for this reason, the simplest model for studying an Ising model within field theory is the one that I wrote here, 5 to the fourth, which is also called a Landau model, after all. And you might have seen this already in the past. However, you can think of different physical systems with different symmetry, and then you might get like 5 to the cube. And the only important thing is that the largest power here, this term here, in this case 5 to the fourth, must be even if you want the energy to be bounded from below. If you get an odd power as a highest polynomial term in a Hamiltonian, then you get an infinite negative contribution to the energy, and the system is not bounded from below, it doesn't have any equilibrium. You get like a leaning plane, particles will roll down forever. And then we added one more piece of ingredients, and we say, okay, sometimes it's interesting to study the effect of an external source which is breaking the fundamental symmetry of my system. And this is interesting both for physical and for mathematical reasons that we'll discuss today. So sometimes it is useful to add here a term in the form d3x j of x phi of x. Now, this term here is breaking the symmetries of the internal interactions, but it's okay because it's the effect of interacting with an external field. Okay, now this is the Hamiltonian we're going to play with as we will develop tools to solve field theory. And I want to stress it is not the only Hamiltonian there is in field theory. You might have Hamiltonian with vector fields, and occasionally, even in statistical mechanics, there have been applications of fermionic fields, but I'm not be concerned with that in this course. If you're interested in that, look at some recent review on polymer field theory, and you'll find some. Okay, fine. So having said all this, we came up with the final. We came up with the following final expression the other day, that the partition function of my system can be expressed as an integral over fields, all the fields configurations. So if I label with 1, 2, 3, 4, 5, all the lattice sides or lattice center, depending if I want to label it at a corner or in the center of the square, that's an arbitrary choice. Then my field phi of x is really a discrete index, which basically tells me where I am on a discrete lattice. And in the continuum, so this is nx, and y, and z, which is telling me, or if you want, I, j, k, which is basically three discrete indexes, the point where I am in the lattice, in the discrete lattice, maybe here, or here, or here. And if I integrate over all the possible values of this tensor, in other words, I integrate on the value of the field in each of these corners on a grid, then the result is an infinite or very large collection of integrals. And in all respect, this is a functional integral because it's an integral of a function phi of x. So that's why I use the same notation for the partition function over fields that we use for the Feynman's propagator in quantum mechanics. And then I have my Hamiltonian. Remember, I did not explicitly write beta. I'm measuring energies in units of kT for simplicity here. And then I want to take on a separate footing the source term. I'm using here a specific notation. When I say A capital dot B, I really mean integral over x of A of x, B of x. I'm using a vector product type of notation to think about all the different values of these fields as components in a vector space. Now, once you include interaction with the source, then your partition function depends on the source, on the value of the external source you use. We mentioned that in the specific example of the Eisen model, the source could be a magnetic field. And so it's up to me to choose how the magnetic field that I apply on my system looks like. It could be flat and constant everywhere, or it could be maybe constant in a cylinder and nearly zero everywhere. And depending on how I choose to play with the knots and details of the magnetic field, I get a different statistical systems because my spin will thermalize accordingly, and therefore get a different partition function. Now, why do I want to? Why is it so important to consider a family of partition functions that depends on the external fields rather than focusing on the black partition function here in the absence of the field? This will become clear at the end of this lecture. And let me already mention that this guy here, meaning the partition function of my system in which I linearly couple my fields with an external source, I want to emphasize linear coupling. This object is called the generating function. And the reason this is called the generating functional has to do with the fact that with this function alone, you can essentially describe all of the physics that is encoded in the Hamiltonian. So in other words, the entire equilibrium statistical mechanics of the theory defined by the Hamiltonian functional H is completely included in the generating functional. So what it means exactly is that if you can calculate the generative functional for arbitrary j, then what you have access to is the complete set of correlation functions in my system. This sounds like a rather obscure sentence. Let me tell you what I mean if my computer wakes up. Okay, so in quantum mechanics, in statistical mechanics, basically all we care of are correlation functions, endpoint correlation functions, thermal averages of function of the fields. So in general, since the fields are my only dynamical variable, I want to compute thermal average of a functional of a field. Now, remember, we are working in a regime where fields are typically small valued. Why? Because of the central limit theorem and because we think the average value of phi is in normal conditions unless we have spontaneous symmetry breaking, but even in the presence of spontaneous symmetry breaking, the typical values of phi are very small. So if this is the case, then this is really a polynomial. You can Taylor expand the functional. So basically, you can relate this to their Taylor expansion somehow. Average it. So all I'm trying to say in this discussion, if I can wake up my pen, hold on one sec, let's see if it works. No, probably my pen is actually dead. All I'm trying to say is that if you can solve, I'm using my fingers now to draw, so I'll be a little bit bad. My hand script will not be very, very good. But once I can compute, say 1, phi 1, phi 2, an arbitrary power of fields, and I call this the endpoint correlation function, x1, xn, then basically I have exhausted all the physical content of my theory. There's nothing more to compute in the theory than this. So the question is, of course, how can you calculate these objects? How can you calculate correlation functions of products of fields, of n products of fields potentially in n different points? Now, graphically, this object is often represented in the following way. You stick a ball, which represents all the possible correlations you have in the system, and you attach to the ball n legs. And at each leg, you attach a label x1, x2, x3, all the way to xn. So what this is basically telling is what is the correlation of the values in fields in different positions. In particular, for instance, if you have a two-point correlation function, then you have the average, the thermal average of the product of the fields. Now, normally in field theory, the correlation function and the endpoint function are not exactly the same, because the correlation function in statistical improbability theory is actually defined by the average of the product minus the product of the averages. Now, if you have some experience with the ferromagnetic transition, you might learn that these two might not exactly be zero in the presence of what is called spontaneous symmetry breaking. So there are situations in which you do develop non-zero values of the magnetization. However, so in most cases, when the field values are actually zero, you don't care about that. So we're going to make a distinction. We're going to call this guy G2, and we're going to call this guy pi2, or phi1, phi2. We can use different notation, of course. I just want to distinguish and be as general as possible. I call G2 the two-point correlation function, not simply, sorry, that's the other way around. To be consistent, let's call this pi2. And let's call this G2. In most of the notes of the course, you will not see this distinction simply because we will not be concerned with systems where these values here are non-zero. For instance, if you are in the paramagnetic phase of field theory, then you don't really care, because in the paramagnetic phase there's no spontaneous magnetization, and G2 and pi2 are the same thing. So most of the time you don't need to worry about this. I'm only bringing this up here because there are a few cases in which you might be having to distinguish. So everything that we have said so far in this lecture is that solving a statistical field theory corresponds to being able to compute arbitrary correlation functions. Endpoint correlation function, let me call it Gn, because if you can get a Gn, of course you get a pi n, because Gn includes G1 and the pi n contains G1, right? So solving a statistical field theory is computing correlation functions. And now, for those who are doing quantum field theory, let me also say that solving a quantum field theory, which we shall see at the end of this course, looks completely analog to statistical field theory in imaginary time, as we already should expect from our discussion on Feynman's path integral in imaginary time. Well, for a very similar reason, and I might get the time to discuss that during the course, solving a quantum field theory is equivalent to computing time-ordered, in that case, correlation functions of fields. And all the physical inputs, physical content of the physics, content of a theory is completely revealed once you know all the correlation functions in the system. There's a theorem for that in quantum field theory. So I made a statement before, and I'm ready to motivate that. And the statement was that if you can compute the generating functional, then you have solved the quantum field theory. So let me remind you what the generating functional is. We wrote it a couple of minutes ago. It's the partition function of the system in which I have added a term that contains an external source, and I'm considering the partition function as a function of the externals. And the statement is, once again, if you can compute this, then you have all the partition functions, you have all the correlation functions you want. And if you have all the correlation functions you want, then you have solved the theory. So solving the theory really means computing this. So it's time to prove this sentence that I repeated over and over. Well, I am a practical guy. You can get this induction theorem type of approach. Induction theorems are great. They are powerful. I like to see things in action, starting from simple to complex, so that you can really see what happens. So rather than going through a formal induction theory, I'll give an example. Suppose we want to compute the two-point correlation functions. And let me not distinguish between pi1 and j1. I'll just call j2. Let's suppose for now I'm in the ferromagnetic phase. It really goes through also for in the paramagnetic phase. It also goes through in the ferromagnetic phase where you have a distinction between the pi's and the g's. But let me not worry. Let's suppose we want to compute this guy. Let's define this. Let's define that we want to compute phi of x1, phi of x2. Suppose we need this guy. Well, see, you can get this by taking twice a functional derivative of the field of the generating function now. And then divide by the generating function and eventually set the source to 0. I should mention I'm interested in the correlation function. Suppose in the absence of any external magnetic field, in this case in the absence of any source. If I'm in the presence of any source, I just simply have to add a finite value here, where normally I have the source field. So let's compute this sequence. Now, this is, let me write it again. It's 1 over z of j, double functional derivative with respect to j evaluated in different points, time your partition function, and then at the end of the calculation you set the source to whatever you want it to be. Now, from the structure, remember, when you have to compute the functional derivative, the best thing to do is to discretize and reduce the functional integral as a very large dimensional Riemann's integral, for instance. Now, since z of j is in fact an integral of fields with an Hamiltonian and a linear coupling, I want to emphasize the linearity. So typically what you do when you act on this, you leave the exponent unchanged and you drop the functional derivative of this guy. Now the functional derivative with respect to j1 in x1 of the integral in dx of j of x phi of x is actually, let me write it on the left rather than on the right. How do we know? We can discretize this sum, discretize this, and then only one term in this sum will survive. Stated differently, this is going to be phi of x1. If you're not familiar with functional differentiation, if this doesn't, let me assume for one moment that this mathematical step doesn't look very familiar to you, and let me prove it. So let me prove the following statement. What is d by dj of x of j of y? Because that's what this integral is all about, right? Because the derivative, you can move this derivative inside And remember, this is a derivative as a functional derivative, not a normal derivative, so you can move it inside the integral because it's derivative over functions. So basically, if you think about this in discrete term, this is derivative with respect to the value. So this is the derivative with respect to the value of the k at the side k. So I label all of lattice points in my discrete system. K is the one associated with x. And this is the value of the field in another point. Let me call L. And this will be obviously delta Lk. So when I go to the continuum, this will be a functional delta, a delta function. So the functional differentiation of the integral between a function and another function will produce this. Or stated differentially, the functional differentiations of the functional derivative of y of jy by jx is a delta function. So with this in mind, it turns out, that this double derivative here is actually 1 over z of j integral d phi of x1 phi of x2 e to the minus beta h minus j double phi. Now let's set j to 0. There is a negative 1 to the square here that I'm not reporting explicitly because each time I'm dropping a negative sign here when I activate the derivative, right? But doing it twice won't change. Well, if you're in quantum mechanics, you have i's floating around, then I square is a negative sign, so you have to worry about signs, but not in statistical mechanics. In statistical mechanics, this is 1. And if you do that, then this is clearly the thermal average of phi 1, phi x2. Now, you can write this in a compact sense by saying that what you've done here is actually nothing but, you know, you can generalize this to endpoint function, saying that suppose you want the endpoint function gn of ox g1 gn, then all you have to do is to take n functional derivatives, each one with its own minus sign now, because there could be an odd number of them. So I get minus 1 d by dj of x1, blah, 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 minus 1 d by dj of xn of my correlation of my generating functional z of j, divide by z of j, and then eventually take j to 0. So that's the statement. So if you want to compute correlation function of any order, endpoint correlation function, you can do that provided you know the generating function. Obviously, computing a generating functional is tremendously complicated for non-trivial field theory. And simply this is why solving field theory is not a piece of cake. If we could easily compute this infinite dimensional integral anytime we want, then obviously we would have solved field theory. And any field theory would not rise any problem. Obviously, you can anticipate that field theory are not all exactly solvable. A few of them are, and you learn a good deal from those who are exactly solvable. So we will spend some time in the future in trying to develop methods to solve exactly or approximately field theory. And let me anticipate that a statement, and it's a bit of a provocative statement that I always say. Theoretical physics is a architecture or a monster, as you want to call it, that stands on two legs or two pillars, if you think about it, building on two legs, if you think about an animal. Without this leg, there will be no theoretical physics. And most of the time, any step you make in theoretical physics is by moving one of these legs. And the two legs are Gaussian integrals and Taylor expansions. These are two things that we can do in mathematics which prove essential to develop any physical theory. Well, if you think about it, what do we know in quantum mechanics? In quantum mechanics, we most of the time end up doing either harmonic oscillator or approximation of it. Harmonic oscillations are basically Gaussian integrals and derivative of it because they're mid polynomials. If you look at it, it's polynomials times Gaussians. The ground state of the harmonic oscillator is an integral. And perturbation theory is basically a Taylor expansion. So these two main tools, the ability of performing Gaussian integrals and the possibility of Taylor expansions, are the main tools we have at our disposal that enable us to solve mathematical problems in theoretical physics. And in the next lectures, what we are going to do is to show how in some cases you can actually use this tool. First of all, we're going to look at cases where you can exactly solve the theory, and we will finally tackle the problem of making integrals over fields that are with Gaussian integrands. And then we will see how combining this with Taylor expansion, we can obtain approximate solutions of non-Gaussian type integrals. And then we will work out other type of solutions and do some playing and gaming with field theory. Okay, I think I'm done for today. See you soon.